Welcome back to this series of videos on support vector machines and using them for modelling credits, modelling corporate bonds, other issuers with a tendency to default. You remember last time we just did a broad introduction on how support vector machines work in that lovely and slightly unrealistic situation where your data is nice and linearly separable without having to do anything special to it. And as I said at the time, that's not always going to be the case, and you need to make some adjustments if you are going to be dealing with more real-world examples. So let's dive back into that. So to reiterate, the data I used before was linearly separable in 2 dimensions with a line and 3 dimensions with a plane. 4 dimensions, 4 variables, it's not. So there's 3 ways you can solve that. You move from a hard to a soft margin, move to a high dimension, or use a non-linear model. And today I'm going to be looking at the first of these, moving from a hard to a soft margin. So as you'll recall, if you're working in any number of dimensions with a hard margin support vector machine, what you're trying to do is minimize the norm of beta squared, because that gives you the biggest margin possible, subject to ym multiplied by bold beta transpose xm minus beta naught being greater than or equal to 1. So that's essentially saying, subject to when you map all your points, they're going to lie either above the top margin or below the bottom margin. Now, if you're using a soft margin, you need to use something called a hinge loss function, which is max of 0 and 1 minus ym brackets bold beta transpose xm minus beta naught close brackets. So what's this saying? Well, if you've got stuff which would not be not fall within the upper and lower margin, so it'd be definitely solvent or insolvent, then 1 minus that is going to be negative. So you're going to get something which is 0. What you're concerned about is the stuff which would ordinarily fall within those 2 margins. So we'll give you a value which would be between 1 and minus 1. So in other words, this function that we're looking at, this max function, is going to be 0 if a point is correctly classified, but if it's not, it's going to be 1 minus ym bold beta transpose xm minus beta naught. So then what you've got to do is, instead of trying to minimize the norm of beta squared subject to those conditions, you've got to minimize lambda norm of beta squared plus 1 over m times the sum from m equals 1 to capital M of that hinge loss function. So what you're essentially doing is, instead of just minimizing the norm of beta squared, you're minimizing some weighted average of that and this hinge loss function. So what that's essentially doing is it's saying, what's my trade-off between having the margin as big as possible and having things which fall within this margin. So just to compare again, just so you can look at it visually, hard margin versus soft margin support vector machines. For a hard margin, you're trying to minimize the norm of beta squared, subject to that constraint below. For the soft margin, you're trying to minimize a measure, a parameter multiplied by the norm of beta squared, plus the sum of all of the variables that fall within that margin, which is what that max function is going to do, divided by the number of variables that you've got, the number of firms that you've got. Now, that parameter in the second one, the soft margin, lambda, that's called a regularization parameter, and it determines the trade-off between the size of the margin and the importance of having points on the correct side of the margin. Now, that's not the only way that the soft margin support vector machine is given. Sometimes it's given as a half norm beta squared plus c times the sum from m equals 1 to m of that max function. So the first term is the inverse of the distance between the margins, and what you've got here is a value of c which is actually equivalent to 1 over 2m lambda as a regularization parameter. So it does the same job, but it is it's inversely proportional to the lambda. And what this means is that sometimes you'll talk about what happens when the regularization parameter gets bigger, and you'd expect what happens when the parameter gets smaller. It often just means that it's been defined differently. So when you do come across this and someone starts talking about this parameter, make sure you understand which flavor is being used, or it might lead to some confusion. So this is what the support vector machine calculation in Excel looks like, with two variables and when you need to use a soft margin. So I've used the data for the same 50 firms, some of which are solvent and some defaulted, various financial ratios, and that default value for that green variable, which would have meant that it wasn't linearly separable before, I'm now making sure it isn't linearly separable, so we have to use this soft margin approach. And this is what the calculations look like in Excel, which are pretty similar to before. You've still got the normal beta squared there, which is the sum product of f to g, so essentially f squared plus g squared. And you've got this value of lambda, which I've called 0.0001 in this example, and then a number at the bottom, which is those two multiplied together, which is how you saw it in the SVM soft margin example. Then this value here is slightly changed from what it was before. This is this max function. It's the maximum of 0 and 1 minus a2, which is the default marker, multiplied by the sum product of B2, C2 and F2, G2, so those two sets multiplied together, minus beta naught. So this is the new parameter, or the new formulation that we're looking at. And what we've got here is what we're going to be sticking into our optimizer, which is G6, which is lambda multiplied by the normal beta squared, plus the sum of all of those variables below divided by how many they are, so divided by capital M. And if you run that through the optimizer and you try to make that as small as possible, what you get is this kind of soft margin line. And you'll see that what happens is the smaller that regularization parameter, the less tolerance you have for points on the wrong side of the margin. So you can see there that if we move from lambda equals 0.00001 to lambda equals 0.001, you find more points are on or even the wrong side of the margin compared to when you've got that very, very strict parameter there. So that's what that regularization parameter does. It changes how that trade-off is between the width of the margin and your tolerance for having things on the wrong side of the margin. So that's where I'm going to leave it for today. Next time I'm going to take a bit of a detour into a different sort of optimization approach for the support vector machines, which it does get a bit technical, but it becomes very useful for some of the stuff that we're doing later on. So enjoy the fact that this is a relatively light session, and we'll be diving a little bit deeper next time. Thank you very much.